This is the video for section 7.1 notes, slides 2 through 6. All right, so in section 7.1, we are talking about series and series notation. All right, so you may recall series from pre-calc where we use this capital letter sigma. It kind of looks like an E. All right, so this is known as sigma notation or series notation, and it refers to the summation. So you'll recall that if I have this sum from k equals 1 to 5 of k cubed, how do we actually figure out what the expansion is? All right, and then find the actual sum. So this is a sum in and of itself, and it has a numeric value. All right, but we need to write out the expansion to show that we understand what the notation really means. All right, so remember, this is the starting value of the index. K would be the index in this case. So that means you're going to plug the starting value in for k. So 1 cubed. All right, then the sigma tells you to add that to, well, the next value after 1. So that would be 2. 2 cubed. Then you're going to add that to 3 cubed, and then 4 cubed, and then 5 cubed, and you stop when you reach the number on the top, right? So that's the initial value and then the final value, all right? And so this would be the expansion, right? And then, of course, this sum is, well, just the sum of these values, right? So this would be 1 plus 8 plus 27 plus 64, and then plus 125. So 9 plus 27, 36, plus 64 is 100, plus 125. So 225 would be the sum. So you need to be able to give the expansion, right? That shows you understand the sigma notation. All right, and then obviously you should be able to find the sum. All right, and as numbers get bigger and bigger, obviously, like you don't have to worry necessarily about calculator, non-calculator. Just understand that you need to be able to find that sum. All right, next one. Write the sum from k equals 5 to 10 with an initial index value of 2. All right, so what we're saying is instead of going from 5 to 10, we want to start with the sum from k equals 2 to something. All right, so if I go from 5 to 10, how many numbers is that? Well, a lot of people say, oh, well, 10 minus 5 is 5. Well, yes, that's true, but remember, you're starting at 5 and you're ending at 10. So you actually have to include those. So 5, 6, 7, 8, 9, 10. There's actually 6 values, right? So that means if I start at 2, then how high do I need to go up to? Well, you need to go up to, well, 7, right? Because 7 minus 5 is 2, right? But remember, that would include. So 2, 3, 4, 5, 6, 7. Right, so you're going to 7. Now, how did I get that? Well, if I went from 5 to 2, I subtracted 3. So if I go from 10, I subtract 3 to get to 7. All right, so that's easy enough. All right, now, if I subtracted 3, what do I have to do to the 4k minus 3? So remember, if the first number I'm plugging in is 5 initially, I'm going to get 4 times 5 minus 3, right? I'm going to get 17, right, as my first value, right? But if I plug 2 in, how do I deal with plugging 2 in when I should have gotten 5? All right, so if I plug 2 in, so that's going to be k, what do I have to do? Well, I actually have to add 3 to it. Then I'm going to multiply that result by 4, and then I'm going to subtract 3. So this would be this same summation, but with an initial index value of 2. Now, it is interesting because if you have 4 times k plus 3 minus 3, you would want to simplify that to write it as the sum from k equals 2 to 7 of, well, I'm going to distribute the 4, so I'd get 4k, right? And then if I distribute the 4, I get 4 times 3 is 12 minus 3. That would actually be 4k plus 9, right? And so what you want to do is you want to make sure that you would actually get the same value. So 4 times 2 is 8 plus 9 is 17, so that would be the initial value, right? Then if you plug 6 and 7 and 8 and 9 and 10, these two summations would be equivalent, right? They would have the same value. These are numeric expressions, okay? All right, next one. Write the sum from k equals 1 to 7 of k squared with an initial index value of 3. All right, so what does that mean? Instead of sum from k equals 1 to 7, I'm going to start with k equals 3. So what did that mean? Well, I added 2, right? So I went from k equals 1, now I'm at k equals 3. So 1 plus 2 is 3. So that means I'm going to go, instead of up to 7, I'm going to go up to 9, right? All right, so now, since I added 2, what do I have to do to k to make sure that now the first value I plug in ends up being 1, right? So what do I have to do? I have to take k and I have to subtract 2. So important to note, if I'm going to shift the index by positive 2, then I have to shift the value here by minus 2. All right, now, the way to think about it is when we were doing like graphical shifting, so like if I had f of x, right, and then I wrote f of x minus 2, what did that actually do to the graph? It actually moved it to the right 2, right? So here, if I took k and wrote it as k minus 2, I've actually shifted to the right. So that means I went from 1 to 3 and 7 to 9. So that's kind of the idea there, all right? So you may or may not recall that from pre-calc, all right? But we just want to have just a reminder and a little bit of understanding about sigma notation, all right? Now, a couple other things. A couple of these on the next slide are reminders. A couple of them are new to you, but we're going to use them for some of the problems in this section, all right? So the first one, the sum from k equals 1 to n of c. So c is a constant, right? It's unspecified, but that's not relevant. It's not the value of k, right? So when I say for the sum from k equals 1 to n, well, I would plug 1 in, but I don't have a k, so there's no value to plug 1 in. Then I would plug 2 in, but there's no value to plug it in, and 3 and 4 and 5 and 6, all the way up to n. So that means that the first term is just c, and the second term is c, and the third term is c, and the fourth term is c, and the fifth term, and the sixth and seventh and eighth and ninth and 10th and 11th, all the way up to n is c. So what does that mean? There are n c's being added together. So this sum is simply just c times n. All right, here, okay, I have the sum from k equals 1 to n of c times a sub k. So k is a subscript. So that means the first term would be c times a sub 1 plus c times a sub 2 plus c times a sub 3, and so on until you get to n, and you would get c times a sub n. So what you should realize is that every one of these terms, all these things added together, have a c. So we could factor it out. So we could actually write this as c times a sub 1 plus a sub 2 plus a sub 3 plus and so on up to n. So what does that mean? Well, that means that the c could actually be just brought outside of the summation. All right. Now, you may recall from Unit 6, that's actually the exact same way that an integral works, right? Where a constant can be brought outside of an integral. All right. 3, okay, the sum from k equals 1 to n of a sub k plus or minus b sub k could be rewritten as the sum from k equals 1 to n of a sub k plus or minus the sum from k equals 1 to n of b sub k, right? So we're really just splitting up into two separate summations, just like if I had the integral of f of x plus g of x with respect to x, I could rewrite that as the integral of f of x with respect to x plus the integral of g of x with respect to x, right? So very similar. Now, what you do not see listed here is if I had something a sub k times b sub k, you cannot split those up into two separate summations, just like if you had f of x times g of x, you could not split those up into two separate integrals. So they work in almost the exact same way. All right, the next one, number 4, the sum from k equals 1 to n of k. So what would this be? Well, this would actually be 1 plus 2 plus 3 plus 4 plus and so on up to n, right? So the sum of the n characters, well, that would be n times n plus 1 over 2. Now, we've actually seen this before in a slightly different fashion. This was the sum of an arithmetic sequence, right? And in pre-calc, we might have written it something like n over 2, right? Number of terms divided by 2 times the first term, a sub 1, plus the last term, a sub n. You should recall that formula, the sum of a finite arithmetic sequence. All right. Now, this is exactly the same because, well, n divided by 2, you see that, And then n, which is the last term, plus 1 is the first term, right? So this is just kind of a more specific case than that that we did in pre-calc. All right. Now, number 5, you would not have seen before. But basically what we're saying is if I took 1 squared plus 2 squared plus 3 squared plus 4 squared plus and so on up to, well, n squared, that sum is always going to equal n times n plus 1 times 2n plus 1 divided by 6. Right? So we're just going to use that for a couple of these problems here, and it's going to help us to develop something that is very important this unit. All right, so number 4. All right, write the sum from k equals 1 to n of k squared minus 6k minus 8 in terms of n, meaning not as a sigma notation anymore, but in terms of, well, the number of terms, right? So if I put 5 in, then I could just plug 5 into my formula. All right, so first thing we do, we realize that this is like number 3. I have 3 things added or subtracted together inside of a summation, so we can say that this is really the sum from k equals 1 to n of k squared. Then minus, now I have 6k, so I'm going to have the sum from k equals 1 to n of 6k minus the sum from k equals 1 to n of 8. All right, so 3 separate summations. All right, now the first one, well, that operates exactly like number 5, right? So that first thing is going to become n times n plus 1 times 2n plus 1, all divided by 6, minus. Now, what happens here? Well, this starts off like number 2, right? We can bring the 6, out front, so it's minus 6 times the sum from k equals 1 to n of k. Well, what is that? Well, that's actually number 4, right? So that's going to be 6 times n plus 1 over 2. All right, and then lastly, minus the sum from k equals 1 to n of 8. Well, 8 is a constant, so this actually works like number 1. So it would be 8 times n, so 8n. All right, and so now this sigma notation is now written in terms of n, right? So if I said, oh, I wanted this sum to be from 1 to 10, then I would just plug 10 in for n, and then I would have my value without having to worry about the, the sigma notation expansion or anything like that. All right, so we want to be able to do that because that is going to be really big for something that we're going to do in a few slides. All right, so now let's put kind of that aside for a minute. Hopefully we recall that. All right, and then let's talk about where we're actually going with this, okay? So number 5 here says, estimate the area under the curve y equals 8 minus 1/2 x from 0 to 16 using 4 inscribed rectangles of equal width. All right, so what we want to do, we want to draw a graph of y equals 8 minus 1/2 x. All right, what is 8 minus 1/2 x? It's a line, y-intercept of 8, slope of negative 1/2. All right, so we draw that graph, okay, starting at 8 here, right, and it has a slope of negative 1/2, so it's going to go like that, and it's going to end up all the way over here at 16, 0, right? If you think about it, 8 minus half of 16, so 8 minus 8. All right, so we're starting at 0, 8, and ending at 16, 0. All right, so now it says we're going to estimate this area. Okay, now, yes, this area is a triangle, okay, and I understand that, but I am telling you to estimate this area using 4 inscribed rectangles. All right, so what does inscribed mean? It means that it is drawn inside of the shape, all right, and it says using 4 of these rectangles of equal width. So that means I'm going to go from 0 to 4, 4 to 8, 8 to 12, and 12 to 16, right? So I'm going to draw a rectangle inside of this shape, okay? Then from 4 to 8, I'm going to draw a rectangle inside of this shape. And then from 12 to 8, I'm going to draw a rectangle inside of this shape. And then the last one, I'm going to draw a rectangle inside. But it actually has 0 height because I'm starting at 16, 0. So it looks like that. All right, so now how do I find the area of these rectangles? All right, so the area of the rectangle, well, I'm going to take the width, which is 4, right? 4 for each of them. And I'm going to multiply by the height. So how do I find the height? Well, I'm going to take that x value, 4, and plug it into my equation. 8 minus half of 4. 8 minus 2 is 6. So this thing is 6 units tall, 4 units wide, so it has an area of 24. So we're going to take 24, and we're going to add it to the next one. So it's 4 wide again. And now this is 8 comma what? 8 minus half of 8 is 4. So it's 4 wide, 4 tall, so it has an area of 16. So 24 plus 16 plus this one, 4 wide once again, but now 12 comma 8 minus half of 12, 8 minus 6 is 2. So this is 2 tall, 4 wide, so 4 times 2 is 8. And so 8, and then the last one, well, it is 0 tall. So it's 4 wide, 0 tall, so it has a area of 0. All right, so 24 plus 16 plus 8. So we get 48, right? All right, so now that is our estimate of the area under the curve using this process. Okay, now, yes, I understand it is a triangle. We could find the area exactly, okay, but as we move forward, that is not going to be the case, and I'll show you that on the next slide. All right, so 6 says estimate the area under the curve, y equals 8 minus 1/2 x from 0 to 16 using 4 circumscribed rectangles. All right, so same graph, all right, but now a circumscribed rectangle. What does that mean? Well, that means the rectangle is drawn to the outside of the shape. All right, so this is 16. So once again, here's 8, here's 4, here's 12. All right, so now this is 0, 8. All right, so now I'm going to draw a rectangle, but it's going to be circumscribed. So that means I'm going to go outside of the shape. Okay, so then 4 over to 8 outside of the shape, 8 over to 12 outside of the shape, and 12 over to 16 outside of the shape. So once again, I'm going to take the width and multiply by the height. All right, so what's the height of the first one? Well, the height of the first one now is based upon this value on the left of the rectangle, and so its height is 8. So it's 4 wide, 8 tall, so 32, right? So we're going to take 32, and we're going to add it to this one. 4 wide, how tall? Well, remember, this point, we already figured it out. It's 4 comma 6. So now it's 6 tall, 4 wide. So now this area is 24. The next one, we've already figured that out. 8 comma 4. All right, so it is 4 tall, 4 wide, so 16 in area. So 32 plus 24 plus 16. And then this last one, 4 wide, but now how tall it is? Well, this point is 12 comma 2, so it's 2 tall, so 4 times 2 is 8. Right? And so now I'm going to add this together. 24 plus 16 plus 8 is 48. But then if we had another 30, now we get an area of 80. All right, so now what can you say confidently? You can say that, well, the actual area under this curve from 0 to 16 is not 48. It's not 80, right? You know it's not 48 because we're missing that and that and that and that, right? Okay, you know it's not 80 because we've added extra value here, 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 and here. All right, but what can you say? Well, it's got to be in between those two, right? One of them is an upper estimate. One of them is a lower estimate, right? Now, it obviously happens to be because this is linear, right, that it would be the average of those two, right? So, yes, we could say, okay, well, it's going to be 1/2 base times height, right? Or, add those two together, divide by 2, right? But remember, if it wasn't linear, that is not going to be the case. So let's take a look at our next example, slide 5. All right. It says estimate the area under the curve y equals 16 minus x squared from x equals 0 to x equals 3 using 3 inscribed rectangles of equal width. So I actually started it off. I already have a picture here. So go ahead and draw this picture. We're going from 0 to 3. Right? So that means each one of these is just 1 unit wide, right? Nice and easy. 1 unit wide. All right. Now, how tall is it? If this is an inscribed rectangle, we're basing the height on the right side of the rectangle here. All right. So the right side, well, if I plug 1 in, I get 16 minus 1 squared. Well, that would be 15. Okay, if I plug 2 in, I get 16 minus 2 squared, so that'd be 12. If I plug 3 in, 16 minus 3 squared, 16 minus 9 is 7, so 3 comma 7. All right, so what's the area? Well, this is 15 tall, 1 wide, so it's 15. This is 12 tall, 1 wide, so it's 12. This is 7 tall, 1 wide, so it's 7. So the area under the curve from 0 to 3 is going to be 15 plus 12 plus 7, right? So 15 plus 12 plus 7. So 15 plus 12, 27, plus 7 is 34. 4. All right, so that's our estimate. Now, we know that the actual value is going to be greater than 34, right? Because we have missed these values by using inscribed rectangles. All right? So now what if we went to slide 6 and we said, okay, well now let's estimate this same area using 3 circumscribed rectangles. So now I'm going to base the height on the left side of the rectangle. So once again, I'm starting at 0. I'm going to 3. So 0 to 1, 1 to 2, 2 to 3. So once again, all 1 wide. Okay. But now, what's the height of the first one? Well, this point is 0, 16, right? This one, once again, is 1, 15. This one is 2, 12, right? And this point over here, the 3, 7, is not relevant in this particular problem. All right, so now the first one is 16 tall, 1 wide, so it's an area of 16. The next one is 15 tall, 1 wide, so it's an area of 15. And then the last one, 12 tall, 1 wide, so area of 12. So 16 plus 15 plus 12, right? So if you do that, right, you get 43, right? So now, what do we know about 43? Well, we know 43 is an overestimate because we've added these values on, right? Now, what can you say? You can say that the true value is going to have to be between 43 and 34, right? You know 34 is an underestimate. But is it the average? The answer is no, it is most certainly not the average. Why? Well, because this is not a line, right? So if you were to kind of like zoom in, so let's just take like this little spot right here, okay? And I'm going to draw it, but like kind of zoomed in, all right? So you've got the curve right here like this, right? Then you've got the point that would be like your 115, and then your 0, 16. All right, now, the first rectangle was like this, right? It was down here. The next rectangle is like this. So now, let's think about it, right? This area that you've missed in the first estimate is greater than the area that you overestimated in the second rectangle, right? Everyone see how that area below is very clearly bigger than the other one? All right. So now that has to do with the fact that this curve is concave down, right? Because if it was concave up, it would actually be the other way. All right. So what can we say? Is the overestimate, the 43, closer to the true value, or is the underestimate, the 34, closer to the true value? Well, our underestimates were greater than that of our overestimates. And so that means that the actual value is slightly closer to 43 than it would be to 34, right? All right. So now, this is just estimating area under a curve using rectangles, okay? All right, so now, let's take one more, all right? So it says, estimate the area under the curve y equals x squared from x equals 1 to x equals 5 using circumscribed rectangles. All right, so first of all, we've got to draw a graph. So y equals x squared, okay? What is y equals x squared? Just a basic parabola starting at 0, 0. All right, so we draw that. All right, now, we want to go from 1 to 5. So I'm just going to put 1 here, and I'm going to put 5 here, right? Now, all it says is using circumscribed rectangles, right? So what does that mean? Well, it doesn't tell me how many to use. So could I just use 1? Could I say, oh, okay, well, from 5, I go over and I draw 1 rectangle, right? And what is this point? This point is 5, 25, right? 5 squared. All right, so this is 4 units wide, and it is 25 tall. So my estimate is 100, right? Well, that's a terrible estimate. Why is it a terrible estimate? Well, because this area is what I'm trying to estimate, and this area is actually larger, right? So what does that mean? Well, that means that my 100 is like well over double the true value. So it's really not a good estimate, right? So yeah, we probably wouldn't use 1 rectangle. So what's going to be a better thing to use? Well, okay, is 2 rectangles going to be better, right? So now if I draw that, it would go from 1 to 3 and from 3 to 5. So now I go over here, right? And 1 to 3 and 3 to 5. All right, so that would be better, right? Because now I don't have all of that, right? Okay, but, well, what would be even better? Well, I guess more rectangles, right? So, okay, what about, like, instead of 2, what if I went and did 4 rectangles? 1 to 2, 2 to 3, 3 to 4, 4 to 5, right? So now I have 1 to 2, 2 to 3, 3 to 4, 4 to 5, right? Now, is that going to be better? Well, yeah, of course it's going to be better, right? So the question really is, how can the estimates get better and better and better and better? Well, really, the key is use more rectangles, right? Right? Because if I use 4, well, it's going to be a lot better than using 1 and a lot better than using 2, right? Well, okay, so 4 rectangles, can I use more, right? Could I use 8 rectangles or 16 rectangles or 100 rectangles, right? So really the idea is use more rectangles. But what's practical? Well, 4 is practical, right? That's not too bad. So let's actually do this work, right? I'm going to take the width of 1 and multiply it by the height. Well, what would the height be? Well, the first height is based upon 2, right? So it'd be 1 times 2 squared, right? Then plus 1 times 3 squared plus 1 times 4 squared plus 1 times 5 squared, right? So that's going to be my estimate using 4 rectangles. All right, so 1 times 2 squared, so 4 plus 9 plus 16 plus 25, right? So 4 plus 16, 20, 29 plus 25, right? Gives me 54. All right, so 54, that's my estimate. Remember my initial estimate was 100, right? 54 is certainly much better, but we know that 54 is what? Well, greater than the actual value, isn't it? All right. Why? Well, because we have these overestimates, right? Now, if I would have used Inscribed, well, yeah, we would have had an underestimate. Okay, so that's what we're doing at the beginning of section 7.1. All right, so keep in mind the idea of using more rectangles as we continue in 7.1.